Ballering. I'm a Virginia Initiative on Cosmic Origins Fellow at the University of Virginia. And today I'll give you a first look at some disks and proplyds in the ONC with some new ALMA data at 3 millimeters. I'll say that this is a first look, so the data are not published, so you can think of all of this as a bit preliminary. So the story starts a few years ago when Josh Eisner led a program to mosaic the inner 1.5 by 1.5 arc-minute region of the ONC with ALMA at band 7, so that's at 850 microns. They detected over 100 in sources, and one of their main results is that the disk sizes were quite small. You can see that on the cumulative distribution to the right here, where the ONC disk sizes are shown here in red, and you can see the distribution has shifted towards smaller disk sizes compared to disks seen in lower mass star forming regions. And so that was taken as evidence that they are being truncated by external photoevaporation. So then we went and got some follow-up data. This is, again, at ALMA band 3 at 3.1 millimeters, mosaicing that same inner region of the ONC. And so we achieved a spatial resolution of about 60 milliarcseconds, which corresponds to about 24 AU at 400 parsecs, a sensitivity of about 30 microjanskis per beam, plus or minus that, as the noise varied across the mosaic. And our goals were to measure the disk masses and sizes in band 3, and as well as to get the spectral indices by comparing with the band 7 data. So the disk masses we get are, derived from this formula, which assumes the dust emission is optically thin, and we have to make some other assumptions, of course, about the dust temperature and the opacity. So take those masses with a healthy amount of uncertainty. And so here are 4 proplyds and what they look like in our data. This is sort of a subset of our results that I'm going to share today. And at the top here, you'll see the view you're probably most familiar with from HST of these 4 systems. And at the bottom, you can see the images that we've seen at band 3. And the nice thing about working at band 3 is that we're sensitive to both the free emission from the ionized proplyd as well as the dust emission from the disks in the system. And so if you look at the images, you can see two peaks of emission in each proplyd. The shell at the front is from the free, behind it is the disk. And to drive this point home, I've overlaid on each of these images these red contours, which are the 1.3 centimeter images from the VLA that were published by Patrick Sheehan several years ago. And you can see they peak right on this front edge, overlapping with the head of the proplyds. And then in these black contours is the what we see in the band 7 ALMA data, and this is picking up the dust. And so the nice thing here is that we have the spatial resolution to spatially separate the free emission from the dust emission in these systems, and we can do a better job of isolating the disk and measuring its properties on its own. So, I picked these systems because, we can zoom in on the disks in systems that are, truly being threatened by their surroundings, evidenced by the fact that we do see this photoevaporating proplyd. So measuring just these dust disks here, the sizes are fairly small, 13 AU, 17 AU, 34 AU. That's generally in line with the sizes measured from the band 7 data. The dust masses are not terribly small, tens of Earth masses or a little over 100 Earth masses, although of course there's some systematics in how that calculation is done. And the spectral indices were also found to be quite small, between band 7 and band 3, about 1.6 up to about 2. So I want to talk a little bit more about the implications of the low spectral indices. So I'll first note that, they're on the lower range of what we've seen for spectral indices from disks, but they're not completely unheard of. So there's this nice recent work by Tazari and collaborators compiling the spectral indices out to 3 millimeters for disks in several low mass star forming regions. And you can see that, there are disks in these other regions that fall down around 2 or even slightly below. So our disks are not totally out of alignment with what's seen in other regions, although it's at the lower end of the distribution. And the traditional interpretation of a spectral index is that, we think of the dust opacity follows some spectral index beta, and then if the disk emission is optically thin, and we furthermore assume it's in the Rayleigh-Jeans regime, then the spectral index should correspond to 2 plus beta. So we can measure the spectral index, subtract 2, get beta, and interpret something about the dust properties. So in that interpretation, a low alpha corresponds to a low beta, which would correspond to large grains. So you could say that, this is evidence for a lot of grain growth in these disks. But it's more complicated than that, because you can also get low spectral indices for disks that have high optical depth. And I've shown that point in this figure down below. This is the results from a suite of radiative transfer simulations that I published last year. And in each of these plots, the x-axis is the disk size, the y-axis is the spectral index out to 3 millimeters. And there's a panel here for 3 different dust masses in the model. And in these model setups, beta is about 1. So what you'd expect to measure in this interpretation is about 3. But what you actually see from the radiative transfer simulations is shown in these black lines. And as you go to smaller disk sizes, especially for larger disk masses, you can see a large deviation from that expectation, and that's due to the disks being more optically thick. And so that reduces that spectral index down, can get close to 2, and that might be a good explanation, especially since we are seeing that these disks are on the smaller side. There's also a complication from dust scattering. If the grains are large and optical depth is high, the dust albedo can alter the spectral index as well. So there's interpretation of the low spectral indices is a bit complicated. So I'll leave you with my conclusions that we've obtained a high resolution deep mosaic of the ONC at 3.1 millimeters. We see lots of sources, but in a close look at a handful of the Proplyds, we see that the dust emission can be isolated from the Proplyd free emission. We found that the disk sizes are small, which is in general agreement with what we've measured in the band 7 results, and that the band 7 to band 3 spectral indices are pretty small. So I'd say stay tuned as we continue this analysis for all the sources and put it into a more statistical context, and I'll gladly take any questions.